Hi, thank you very much. Hi, everyone. So I'm here to talk a bit about security in general, about how we detect bugs. This particular work is in smart contracts, but I'm going to go a little bit more general and then come back to this. So first, I don't need to say this, but there's a lot of attacks going on. They have been reduced a little bit last year, but this is the numbers from Defilama, and you see the millions of dollars that are reported stolen each year, and this is a lot. There's something that needs to be done. And sorry, there's more to this. If you look at the numbers, you'll see that there's a correlation between the TVL and the hacks. There's also indications that audited code gets less hacked into. So that's why it's important to put at least some security into it. So basically what I'm driving into is you need to lower your risk. And the way to do this is to eliminate threats. So basically, attackers don't need to put a lot of effort. They are going to go into the more easily hackable businesses. And the way to prevent you being hacked is to be more secure than your neighbors, as easy as that. Eventually, if you are a lot more safer than your neighbors, then you are not going to get hacked. And that's why you are doing this. You cannot be hacker-proof, but you can be less, have a smaller risk profile. So how to do this? Well, things should happen in-house. And the best thing you can do is to use a security framework for software development. There's a lot of those available. Simply pick one. And this will involve in-house training, attack intelligence, so knowing your attacker profile, understanding what are the specific threats that you might face, using a secure software development lifecycle, and eventually after the code is done, okay, you can do audits, external audits, bounties, and other stuff that will also improve or remove threats from your attack surface. So how to remove threats internally? That's why we built a tool. We think that developing by using this tool, you will be able to remove some of the bugs so that even if you go into an audit later, the audit team is going to spend less time with those threats that you already eliminated, and you're safer. Also, I also work as an auditor, and it will always be better if you get code that has been vetted before, that has passed through somebody else's eyes, and maybe they have used a tool to eliminate some of the threats. So the threats that still remain in the code are more difficult to find, and the auditor can concentrate in those and not start with the easy things. So what we did in this tool, we try to include the lower hanging fruit, include best practices, include the most common threats. So we did all that. So basically, this tool will detect a lot of these deviations from best practices. It will detect some of the common vulnerabilities. And we have the command line interface version, and it also integrates with VS Code. We are moving into other IDEs as well. We are also including GitHub Actions, so you can include it in your CI, CD. But basically, our idea is for this tool to be as easy to use as possible, not to include false positives. I've been using some tools that are available out there for other smart contract development languages. And when you need to spend a lot of time looking into false positives, then eventually you say, okay, I'm not spending more time with this, and you move on. So it's important that the balance between false positives and detections is good. Thank you. So we spent almost the last 2 years, a little bit more, working on this. As I said, there's a lot of low-hanging fruit out there. So what we did is we went through a list of practices. We went through some of the vulnerabilities that were public. And this tool uses static analysis available from the Rust compiler, some functionalities available from the Rust compiler in order to detect these vulnerabilities. And this tool is called Scout. What's our strategy here? We implemented the detection of some bugs and best practices via first building a list of all these deviations and threats, prioritizing, and then when there were examples available, we used those smart contract examples to build our detection. When there weren't any, we simply developed the smart contracts, including the vulnerabilities. And we did many of these, over 20 of these. And then we built detections for these deviations and these threats. And of course, since we don't only want to detect one example, but any deviation from this, any different way of coding this, the detector tools adapt and we build more examples. Where did we derive these smart contracts and examples from? Well, basically, there's a long history in Ethereum. Polkadot smart contracts aren't do not have that bigger history. So we used many examples from Ethereum. Aleph0 has a good list of threats and best practices, and they have a good history in Ink smart contracts. We did our own audits. We looked into publicly available audit reports and incidents. And as I said, best practices in software development, there's a lot out there, so we use that as well. And this is basically the architecture of our tool. And in here, you see simply contract going into the Rust compiler. The Rust compiler will produce intermediate representations, the abstract syntax tree, a higher level intermediate representation, medium level intermediate representation. And you can get a hold of this using Dylint or Clippy. We used Dylint. We also played with Clippy. Our first version used Clippy. Both tools are able to access the different passes that the Rust compiler is doing. So how the Rust compiler works, it does several passes and it will create more information going deeper. For example, at some point it will expand macros. And you can get access to a representation before expanding macros or after. Sometimes one will be more useful, sometimes the other. And those are the differences between early lint and late lint. And there's also some tainting available in late lint. But that's how we build the detectors. Detectors are pieces of code that you add to a detectors folder or a linters folder in Dylint. Dylint dynamically can access them. So when you run cargo scout audit, it will go through the detectors that already included as part of the compilation. It will go through our newly added detectors, and it will produce alarms when there's something wrong there, or when the detectors read something. Then we produce the output, and of course, as I said, you can either output from the command line or via VS Code. VS Code will produce wiggles over the offending code. It will add a message with some explanation, etc. And we also provide some other output formats like HTML, PDF, and SARF also. We're including also some common vulnerability markup languages. So let's look into one example of a vulnerable smart contract. Here, there's an excerpt of a vulnerable smart contract. What you see here is the use of set contract storage. This is a command that you can use to write into the memory of the contract. And in this case, you see this is unprotected. The function is one simple function called misuse set contract storage. there's a bigger or a fuller example there. And this is an authorization bug because you are checking nothing into who calls this function and where this write is happening. So let's, sorry. So let's say that this is part of a token contract, a ERC20 or some other kind of token contract. And assume that Alice, user A, gives an allowance to user B of 10 tokens, or 1 token, it doesn't matter. But if user B is able to call this function, then he may be able to overwrite the 10 tokens allowances and make something bigger, 100, 1,000, whatever he wants. All of the available tokens that Alice has, Bob can steal. So this is the way to implement this using cargo. Simply what's going on here, it is Bob is calling this command. This 5GJ5 is the contract address, and then the message, it's calling the function, and you see the arguments there. It's a byte stream starting with 25500, and there's a small description here of what's going on. So 255000 is the allowances mapping, and then you see Alice's address and Bob's address represented in as 32-byte number streams. So, and finally the number, the allowance Bob wants. When Bob sends this command and he signs, he's immediately overwriting the allowance that before was at 10, and it's increasing it to 1 million. So as easy as that, the vulnerability is attacked. Let me, and the way we detect this, as I mentioned before, we are using information available from the RASC compiler. It's going to make several passes before generating the WebAssembly. And we'll take a hold of dilint in order to use these representations. So, and basically the logic of our detection is going to be this. We are going to visit the different calls to functions, and we're going to see if at some point it is calling set contract storage. If that happens, then it could be a correct use of set contract storage. This could happen, but only if it's conditional to, I don't know, the owner of the contract being the caller. So if the caller of this set contract storage is the owner of the contract, then okay, he may be able to write into this any position. Else, we should do something differently. And that's the logic of our detector. It's very simple. If set contract storage is called without any conditional, we trigger an alarm. Else, we check if there's a conditional. If there's a conditional, we check what's inside that conditional. Let me, sorry. No. Let me show you the code here. So this is the detector. And you see simply the way the detector works. It's checking if there's a set contract storage there. Let me, and here are the conditionals. So the conditional could have the owner in the left or in the right, and the caller in the left or in the right. So that's how we check for the conditional. Below, we check if the expression is inside a conditional, if there's a set contract storage there, and well, as I said, this is what happens here. If it's not in a conditional and the conditions I mentioned before about the owner and the caller are there, then it will trigger the alarm. If I go down, let me. And finally, this is how we trigger the alarm and the alarm message. So detectors are very easy to build. And there's a lot more vulnerabilities that we build detectors for. I'll go quickly through some of those. Set code hash is something similar. You cannot set a code hash if you're not the owner of a contract. So we'll check for those. Zero or test address is something interesting happening only in Ink, not common in other languages, which is that the private key for the zero address and the test address are known. So if you develop a contract and you forget to prevent users from, sometimes you allow a user to input an address. And you need to check if the user is using the zero address, because since the private key for the zero address is public, anyone can steal funds or can use that key. So that's why whenever you're setting an address variable, you always check if there's a zero or test address used. Integer overflow or underflow. Also, you could use a macro to allow overflows. So if that macro is on and you're allowing overflows, then we're going to check if you're adding to an integer without controlling that. Divide before multiply, that's a precision best practice. Often if you divide before multiplying, you may lose some precision. And the list goes on. There are some Rust-related errors also that we looked into, like when you will panic and the contract will exit without returning an error, or will break the execution. So sometimes you do not want to break the execution of the contract, and you need to catch the error. Reentrancy and delegate call, which are normal to Ethereum and to other development languages. So we also accept contributions. There's a repository here, and no. So if you want to contribute, I'll share the link later, but you could either contribute with detectors or with test cases. The more test cases or the more vulnerable contracts you provide, the better we get out our detectors. For each test case, that's how we call what we call the vulnerable smart contracts. We provide two examples of the smart contract, one vulnerable version and one fixed version. And whenever we compile and we test Scout, what we do is we will check that it detects all the vulnerabilities and it fails to trigger on the non-vulnerable cases. At least those should work. So that's how we ensure that this is at least a little precise. Let me now get back to, sorry. I'll simply close this. This is our documentation and more detailed scenarios, and let's get back to the presentation. So as I was saying, we accept contribution. There's the link. And a little bit about what we did here. Well, this is what I mentioned earlier. We have 20 plus vulnerable smart contracts in that list over there. And our intent in putting this in the public repository is that anybody can use them. So if you build also a tool for detecting bugs in Ink smart contract, this is a test bed that you can use for your tool. And as bigger as this database of vulnerable smart contract gets, the better for the community. And of course, also we built this tool, which is available and anyone can use. This is the Scout team. Facu, Tiki, and Jose are our developers. Valeria here is our business developer. Federico and Matias are product managers. Arturo is our developer relationships, and Ariel, myself, I'm the tech lead. One other thing before I close, we did this with grants from the Web3 Foundation and from LF0, so we thank them for their contributions. And if there's any questions, please ask. This is the download link. Thank you very much.
Okay, so does anybody have question for Ariel? please.
Yeah, thank you for your talk. I have basically two questions. The first is at the beginning of your presentation, you showed a slide where you mentioned, and correct me if I'm wrong, that you use all three intermediate representation of Rust compiler, MIR,
Yes.
HR, and AST. What's the purpose of, and in what case, which one do you use, which representation?
Yes, it depends on the bug, but basically, for example, as the Rust compiler passes, it's going to provide different representations and different details there. So, for example, in the case of the set contract storage, you use the higher order representation because you only need calls to functions, and this is quicker, calls to functions and the conditional, you have the flow of the program there. After that, you do not have the flow because sometimes the compiler will optimize a few things, so you lose some information and you have another information available. And sometimes the AST is all you need. And sorry, there's other cases there I forgot to mention. Sometimes, I don't know, you simply want the version of the compiler that you're using. So if you simply want to learn the version of the compiler, then you're using none of this and you're simply checking the TOML file or whatever. So there's different checks there.
So it doesn't mean that you need to support 3 engines that can parse and operate with all this representation and use that one that you use in your particular detectors, right?
So no, let me.
I mean, isn't it triples the amount of work you need to do?
No. So if you see here, this is the detector for set contract storage, and simply this one uses Rust CHIR, which is the higher.
So you directly call it, right?
Yes.
Okay.
Yes, but it's a macro that you are using for this detector, and the second detector is going to use a different macro. And
okay. I assume maybe you have your own layer of access to it. And thank you. And the second question is, how do you model attacks that involve several contracts, like reentrancy? So you need someone to model someone else who will give you a backcall.
Yes, well, but the vulnerable contract is only one. Only that. Let me show you.
I mean, the chunk can be quite long, right?
Yes, but so this is the folder, and you see there's a detectors folder, and I'm going to close it, and there's the test cases. And as I said, let's go to reentrancy. We have 2 examples of those. So there's the remediated and the vulnerable example, and in the vulnerable example, there's an exploit folder with the exploit. So basically, in here you have the vulnerable smart contract, and possibly the exploit is going to be in the other folder, and you're going to have the second smart contract there, which implements the attack. So all the attacks we can execute. We also include the exploit code for all the vulnerable smart contracts.
Okay. I think I can let anyone ask. Thank you very much.
Thank you.
So, okay, please go on.
So initially, basically, you said that you have a auditor background also. So like, as you guys know, all the points that we would need to basically address for the audits and all these things. So have you guys achieved all these things, or do we have any documentation and all, like the points, the detectors and all you are creating, or the open source community can basically directly work on that instead of finding the detectors by their own?
No, so let me go in here. So this is our documentation, this is our documentation page, and here you have all the vulnerabilities, and the documentation for these vulnerabilities is included here. So I don't know, panic error, there's a description, and we try to add all of the vulnerabilities that we considered into this folder, as new vulnerabilities come, then we need to add those. So whatever we worked on, it's public, it's open source. And when we generate the report, it's going to include the name of the vulnerability, links to some remediation example. Let's see here. So here you have both the exploit scenario, some remediation, references. So whatever vulnerability we consider, we try to document as much as possible.
Okay. Thank you.
Thank you.
So if we don't have any questions for Ariel, we will settle it right here. Thank you, A.
Thanks, everyone.